Carroll Community College has a long tradition of developing and fostering collaborations with the local partners in the community. For the last few years, there has been a push in the sciences, technology, engineering, and mathematics fields called the STEM fields, both at the national level and at regional level in the state of Maryland. It has trickled down to the local level in terms of the public school systems and also at a higher education within our community. For the last few years, Carroll Community College has been involved in partnership with the Carroll County Public School Systems in STEMs, where the students go out and mentor the 7th grade students at Shiloh Middle School. We were informed of a unique opportunity by one of our mathematics adjunct faculty, Mr. Bob McLeod, who is an engineer at Johns Hopkins Applied Physics Lab. The opportunity involved partnering with the APL as a resource for mentoring the high school student population, which also meant that we had to partner with CCPS. And since we had the partnership with CCPS through our Shiloh Ready Set STEM program, it was easy for us to set that partnership with the Applied Physics Labs. Deans Rob Brown and Steve Jeppe, along with the Vice President of Student and Academic Affairs, Dr. James Ball, were highly supportive of this initiative. And hence, STEM camp that involved partnership between an industry, higher education, and public school system was developed at the college. The collaborative effort between the three partners primarily involved the departments of mathematics and engineering, sciences, and education. The faculty members that were involved from the get-go to the end of the STEM camp were Maria Bernes, who is the chair of mathematics and engineering, Ann Davis, who is the chair of sciences, Susan Size, who is the chair of education. Within the college, there's also a collaborative learning environment where the students are the major stakeholders in what we offer to the community. And it was no surprise to us that we had more than 20 students and faculty who volunteered to help out in the STEM camp. They ranged all the way from education majors to STEM fields. The STEM camp collaborators are also very grateful to another area of the college, the continuing education and training, who provided us the conference room at no cost to the STEM camp. We would also like to thank Mr. Dwight Carr, who is the APL STEM manager, along with his staff, who developed the STEM camp in terms of all the legal protocols that had to be followed to meet the Ignition Grant criteria through which the STEM camp was funded.
Welcome to 2012 APL Carroll Community College, Carroll County Public Schools STEM Camp. We have 41 kids here, ranging in age from freshman in high school to senior high school, working at the moment on a conductivity probe, which they're actively designing and building this afternoon. This STEM camp is a collaborative effort between Johns Hopkins University Applied Physics Lab, Carroll County Public Schools, and Carroll Community College. The funding for this camp has been provided by Johns Hopkins University Applied Physics Lab as part of the Ignition Grant program. The lab has made available funds to employees who have ideas that they want to put into action, such as this. So for about 3 months, a team of people from APL, Carroll Community College, and Carroll County Public Schools have been working to put together the curriculum and the program to select the students for this camp and to make it all happen. The theme of today is technology. Each day of the week has different themes. Monday, the theme was forensics. Today, Tuesday, is technology. Wednesday is rocketry. Thursday is cybersecurity. And on Friday, the students will be visiting Johns Hopkins University Applied Physics Lab to get tours of our facilities at APL. As I said, today is the second day of camp. We have 3 more days ahead of us. Everything's going really well at this point, as you can see. Students are enjoying themselves. They're working collaboratively and producing some really good products.
The week-long STEM camp culminated in a field trip from the college to APL in Columbia. When we got to APL, we were able to have a tour of some of their facilities. The tour included high school students being able to see their Mod 6, their environmental test facility, their RPIL, and their electronics lab. The students got a real good look at some of the equipment that APL uses and a good description of some of the things that they do there. After lunch, we were treated to a magic show by one of the APL employees that incorporated some of the STEM concepts that the students were exposed to during the week, as well as an informative session on material science called What is Material Science? We were there for about 5 hours or so, and the students really enjoyed the trip. The students in the STEM club at the college have visited APL in the past and found it very interesting and very applicable to the fields that they want to pursue. Some of the college students were able to accompany the high school students on this particular trip, got to see additional facilities, and found them as intriguing as past trips. We would like to thank Brian Shoemaker of CCPS and CCPS admin for their significant help in arranging the transportation for our field trip to APL. We'd also sincerely like to thank Mr. James Tepe, an APL employee, for his extremely kind donation to pay for the transportation that allowed us to go to APL on Friday and wrap up our week-long camp. CCPS faculty and administration were a critical partner in this camp. Brian Shoemaker, the STEM coordinator for CCPS, developed and led the Tuesday technology session in which students were engaged in hands-on activities from the beginning of the day to the end of the day, including a trip to the stream to collect water samples and making technology to measure characteristics of the water. CCPS STEM teachers and administrators from central office were able to participate and visit during STEM Camp Week. One of the things that was valuable in that was that they were able to get ideas to take back to their classroom, to develop lesson plans, and to share these ideas with their students in the coming academic year.
In the 18 minutes, you're going to build the tallest freestanding structure you can, okay? At the top of this freestanding structure, you are going to mount your marshmallow, okay? You will be judged based on how far above the tabletop your marshmallow is, okay?
3 of these, I guess, and then
So every single one of them would consist of 3 noodles.
yeah, just put it together.
Just remember, we only get 10 strands out that way.
Yeah, it works out perfectly if you have, because there's 30, so you have 1, 2, 3, 4, and then a 5th in the center. So you have 4 going up, and then you tape both or all the pillars down.
Well, we might put it down the middle, because then if you put it on the top, it'll like top.
Well, that's why I put these extra threads out here. And we can always extend these out. You know, we can always add more to the bottom to support. That's why we're testing that. Right. Now everybody leave it alone. Clean it this way more.
I think you're gonna have to. I'm not trusting. Put it
Wait,
down.
hold on, let's turn it. Let go. Just let go. It's
Guys,
still
that'll fall down.
We need
Put
more
that
weight.
there.
I think we should tape these together up here and then just stick the marshmallow on top.
But that's implying it can stand.
Well, it's probably we're not going to be strong enough. We're going to need to put some support down here.
37.5 inches. You ready? That's team 2.
They've got a piece sticking up. So
All right, everybody, come on back.
Team 2, you guys are impressive. What was the world record?
Let me tell you, this one here is like 2 inches short of the biggest one Tom has ever seen.
So today at STEM Camp, this is day 2. Students are focused on technology, innovation, engineering, with a lens towards the environment. We discussed the Chesapeake Bay watershed and how conductivity and turbidity are 2 measures of water quality, and how they're influential in determining policy and taking action towards an improved Chesapeake Bay watershed. You'll see the students today with a design challenge to create their own conductivity and turbidity meters out of a vast array of different materials. Not all groups were given the same materials. They went through an entire planning process to think about how they would solve this problem. And as they're now meeting with some varied success, they'll work to improve and hopefully quantify their devices. We have some existing devices that are pretty expensive here that they can use to sort of calibrate theirs. And we're hopeful that they're going to have some innovative designs using, again, different materials that will hopefully solve their problem quickly. And this afternoon we're going to investigate an actual stream and see how well their devices work and hopefully evaluate the water quality of that stream.
Hi, I'm Alex Medeiros, and I'm a student from Westminster High School. I'm a rising senior, and the STEM camp has a diverse population. There's a lot of there's freshmen through senior grades and students from Howard, Baltimore, and Carroll County. And I heard about the STEM camp from actually a tutor that I was working with for my math level 2 SAT. And she works here, she's Miss Verostic, and she gave me this letter about the STEM camp. And when I heard about it, it sounded really awesome, because I know a few students from Westminster that have parents at the Applied Physics Lab. So I was really excited to go to STEM camp and see these new, get connected with people and maybe get an internship. That was my goal, and going into this summer I really wanted to get an internship, but I couldn't. I made a few connections, but it just didn't work out. And so that's kind of why I came here, to get connected to John Hopkins University and see the Applied Physics Lab in person. And what I want to be when I grow up is a computer engineer. I'm kind of contemplating whether being a computer software, computer hardware engineer. And I plan to go to MIT, that's my goal, but 10% acceptance rate, so it's pretty tough to get in.
I'm Chris Kazarowski.
And I'm Jessica Highland.
We are both former members of STEM Club as well as former officers.
I guess we're going to talk about what STEM in general means to us and what this camp really means to us. I'm going to be majoring in biochemistry at UMBC. Go ahead.
And I'm majoring in chemical engineering, transferring down to New Mexico Tech.
I really wish that they would have had something like this when I went to middle school or even to high school. They had some programs at Tech, but they were not necessarily related to STEM and not necessarily related to maybe something that I wanted to go into. But it was still a good camp. But I really would have enjoyed something like this. We did like crime scene investigation stuff yesterday for a lot of forensic stuff. We're doing electronics today. I'm not sure what we're doing tomorrow.
Tomorrow we're working with rocketry, and then Thursday we're working on cybersecurity, and then Friday everyone's going down to Johns Hopkins Applied Physics Lab for a tour.
It's really important because there is a shortage of jobs in the STEM fields right now, and in the future we're going to be running out of people that are qualified to fill into those jobs. So we're trying to get students interested very early on in those job fields, so we will have the manpower or womanpower to fill those positions.
Like Jeff said, I wish they had something like this when I was in middle school or high school, because I just kind of had to fumble and bumble my way through to find out what I enjoy. And I've had the engineering aspect of it, and I've had the chemistry aspect of it, and that's why I went to chemical engineering, because it combines the best of the things that I enjoy, and I can apply it in so many different fields that I can go from chemical engineering to medicine, or to what I actually want to do is dealing with explosives. And by interacting with these students, we also tell them about the STEM Club and all the things that we've done throughout the time that it's been established, and try and get these students interested and maybe get word of mouth going so that the incoming freshmen to Carroll community can bring in some new ideas to the STEM Club. And everybody's idea is considered, and all thoughts are considered, and then we just kind of have to balance the ideas with the practicality of what we're doing.
one of the great things about this camp as well is it teaches students the whole research process. Just as today, it's like, okay, these are the things that you have to work with. This is the problem that you need to solve. And so you need to choose people on your team that maybe don't think like you do. Maybe it's a good idea to get somebody who can think out of the box, or another person who's more creative, or another person who knows more about math. So to try to get kids to think about, okay, well, everyone's ideas matter, like Chris said, and everyone has a different way of thinking or approaching things, and to try to put them together to solve a problem and to collaborate.
Like Jess was saying, have all these different people, and everybody learns a different way, and they interact in different ways. So you might have a student who excels in the arts, or someone who excels in math or sciences, and by combining their interests and combining their knowledge, you can create new ideas or new methods of doing things.
There's no electricity going to the clips, so therefore there's no potential of premature launch or shock or anything like that. But when I put the safety key in, I have a safety key now. This one has a little audio device and a light. And I'm going to get sufficiently away from you all. I'm going to hold this up here. And I'm going to go count down. 5, 4, 3, 2, 1. Now I'm going to push the button. No longer hear the beep, no longer see the light, right? I'm going to let go of it. So what happened here? When I push that launch button, this launch button has the light in it. It has a very high resistance of electricity too, higher than what this little wire is. So when I press this thing, this button is, that light is bypassed, and all the electricity is going through the circuit into here. And it's attempting to launch the rocket. This did not flare up or launch because the two clips are touching each other. So when the electricity is going from this handheld controller through one clip, out to the other clip, and then back. So it didn't work. It would be what we call a misfire. Now I'm going to separate the clips so they're not touching. And now I'm alleging that when we press this button again, the electricity won't go through the clips, they're going to go through this very thin wire. This thin wire will glow red hot like a light bulb does. A filament would be in a light bulb, but a light bulb has either argon gas or neon, or it's a vacuum, and so you get an incandescent glow. But here we have good old oxygen and nitrogen around us, so this thing should flare up. And so now the countdown is proceeding at 3, 2, 1, launch. Very dramatic. All right, so this is just showing you that we have different varieties of engines. The engines that we're going to use today are B engines. They're called B44. Talked about it in a second. That means that they are between, they have the total thrust or kick in the pants is 2.51 to 5 meters a second. Okay. It has a nose cone. Guess what the nose cone is called? It has a payload section. In this case, it's clear. Guess what we call a payload section? All right. The body tube has a very special name. It's called a body tube. The fins are fins. There are straws used to guide the rocket up its first 2 feet of flight. You're all with me there on that, right? What do we call the straws? Oh, they're called launch lugs. Yeah. All right, you should have a rubber band called a shock cord. You should have 2 mounts for the nose cone, that's excellent, and a nose cone, and an insert tube. It's like a big white cigar band. Folks, first step you're going to get is your engine mount tube and your engine hook. Your volunteer will have made a slice in the top of the engine mount tube, 1/8 of an inch from the top. What you're trying to do is assemble a engine mount tube to hold your engine in, and it'll have the 2 centering rings, the engine hook, and the bottom and the mount tube all together. This is what it looks like when it's finished.
Oh, sorry.
I'll be right back, guys.
This is stabilizing the work. It's probably
Alright, go home. So you want me to send this down so you move curved? Thanks. Like that, I want that bump so you move curved and less. I got more glue over here.
Okay, so now we just need to glue these yellow pieces together. Me too, since it's basically going to be up going underneath. This must be a ring here. This ring. Zach, I'll see you.
Like a G or what's what it's like a double knot. What's a double knot? Is it like a bow? Like how you tie your shoe? Oh, okay, like a square knot?
Fire over there.
I think it was attached. Probably be on the end. The other side. What was that paper before?
We're gonna take that.
What was that paper?
Is this for measuring where the fins go?
That's what he told me to do. Dude, that's what you had.
There you go. That's
Yeah, you can have my car keys and Chris, can you back up his car down? I don't have that Miata lady. And right there, you know what the car looks like? Here, it's like the first space. That's silly. Five, 4, 3, 2, 1.
They're coming back on our head?
This is a radio telescope, so we study the heavens at various wavelengths. We study them at visible light, like what you might see with your eyes. We use the infrared. We also use the radio part of the spectrum. And this is a radio telescope. This is in Green Bank, West Virginia. Anybody been out in that area, maybe camping or something? Yeah, it's a really nice area. It's really quite beautiful out there. It's in the mountains. And this is the 140-foot, which that's what they called it when I used it. Now we've gone metric, so they call it the 43-meter. And these are some of the data that were taken with this telescope. So you can see the top image is looking straight at the center of our galaxy using a radio telescope. The one underneath of it is an exploded star. That's a supernova. That image was made with this telescope. And then you can also look at things in our own solar system. So obviously there's Saturn with its rings hanging out there in the radio frequency. And then we can even look at the sun at radio wavelengths. Slide, please. Another telescope that I've used is the Very Large Array, the VLA, that's in Socorro, New Mexico. Anybody been to Socorro, New Mexico, or anywhere in New Mexico?
Behind you.
Behind me.
I actually go to college there.
You're going to college. You're going to MSU?
NMT.
NMT, okay, fantastic. This is a very different place from where we live. First of all, it's the high desert. I believe that Socorro is at around 5,000 feet, give or take. So around here, we are typically between 0 and 1,000 foot sea level. Our highest mountains in Maryland, I think the highest one reaches something like 3,000 feet. This flat plain here is already at 5,000 feet, and those mountains in the background stick up above that. So they call it the high desert. Very, very dry, no humidity. That's why they put the telescope out there, because the water vapor in the Earth's atmosphere gets in the way of reading the signal. This is the Hubble Space Telescope. I was telling you, we put the Very Large Array at 5,000 feet in the high desert, and we put the Mauna Kea Observatory at 4 kilometers out in Hawaii. But what we really want to do is get entirely outside of the Earth's atmosphere. And that just takes, you can imagine, you look through the Earth's atmosphere, it's like looking through soup. And if you can get that soup out of your way, then you can really see what's going on, because there's nothing between you anymore and the object. It's a vacuum of space. So there's nothing to get in the way of what you're trying to study. And you're trying to study the light that's coming to your detectors from those objects. So I was not in space. I was in Baltimore, which is where the Space Telescope Science Institute is, because of course all of the data that come from the Hubble Space Telescope are relayed back to ground. So at Johns Hopkins University is the Space Telescope Institute, as we call it. Stars get born and die all the time. It's just the natural evolutionary process of stars and systems, okay? Our sun right now is a middle-aged star, so it's kind of halfway through its life cycle. But in the beginning, and also it's important to know that our sun is born out of a generation of stars that had already lived and died. So there was a whole generation before our sun came along that filled our sun, in fact, with materials out of which you and I are made, okay? Because the things that we are made out of had to have been created in an earlier generation. So when the stars start, they're just big clouds of gas and dust like this. This is probably either the first or second most famous picture from the Hubble Space Telescope. This is the best picture we have to date of a stellar nursery. These are just clouds of gas and dust that hang out in the universe, and then something happens to trigger them to collapse. And usually it's a shock wave. I don't know if you've ever been somewhere where you have felt air rush by you, like maybe if you're walking along the street and a truck goes by and you feel the air pushing you, or if you're on a bicycle, it might make you wobble, that kind of thing. That's just the idea of a compression wave hitting into you. And that's what happens to these stellar nurseries. They're just big clouds of gas and dust hanging out there, minding their own business, and a shock wave comes and rolls over them. And when it does that, it causes all the material to get compressed together, and out of that compressed material, stars are born. As the gas clouds start to collapse and the particles bang into each other really hard, what happens is a star is born. It's quite simple as that. As soon as it gets hot enough for the star to turn on, and that's what we say when nuclear fusion begins to happen. That's what makes our sun shine, and that's what makes our sun a star and not just a big old planet like Jupiter. Jupiter is sort of a failed star, if you will. It was trying to become a star, but it didn't get enough mass. As this thing is spinning, because one thing you get to know about in the universe, everything is rotating, everything. The sun is rotating, the earth is rotating, the earth goes around the sun goes around the center of the galaxy goes around the center of the group of galaxies it's part of. Everything rotates in